SwayamPrabha. Digital India. Educated India.
So first we have seen the behavior of composite plies, behavior of individual composite plies with respect to its own principal material direction. So we have seen ply like this, and the plies are all unidirectional, and they have fibers oriented in some direction, and we can call this direction 1, we can call this direction 2, and we have defined properties like E1, E2, nu1 2, nu2 1, G12, which we also call E6, and then we have by applying the plane stress condition, we have got into the constitutive relationship, where we relate the in plane strains defined with respect to 1-2 system to the in plane stresses defined with respect to 1-2 system. Now our problem is that our composite laminate is made of different plies, and each ply can have different fiber orientation direction. So I may have another ply where the fiber is oriented in a altogether different direction, maybe in this direction. So my now 1-2 changes, we can call this as 1, this as 2. So each ply can have its own 1-2 direction. So when we want to analyze a laminate, we need to define a global system, global coordinate system, and better that with respect to that global system we define our properties. So if we suppose I have a laminate which is made of these plies, so better we define a system like this x y, which remains same for all the plies, so which is a global for the entire laminate, and we defined our properties, defined our constitutive law with respect to this x y system. Then we can analyze the laminate. So that will be our today's job. So from the constitutive relation which we already defined with respect to 1-2 system, now will be transferred to the x y system. So we will transform the constitutive relation. Now to transform the constitutive relation, we will start with transformation of stresses. At first we transform the stresses. So we already know that we have a relation in this form. Our Q1 and Q2 are same, so we can write it like this. So we have the relation in this form in the 1-2 system, we have to transform it to x y system. So first we transform the stresses. So first we transform this vector, and then we transform the strains. So we transform these strains, and once we are able to transform this into x y and strain into x y, transformation of this q is easy. So we start with the stress transformation. Now let us imagine that our ply has this as direction 1 and this is direction 2, and we need to convert it to convert the relation to x y. So this we can call theta. So the axis 1 is oriented at an angle theta with axis x, and similarly axis 2 is also oriented at an angle theta with respect to axis y. Now, let us draw a line which is perpendicular to our axis 1. So, this is perpendicular, and similarly draw a line here which is also perpendicular to axis 2, and then we complete this rectangle. আচ্ছা এই ছবিটা আরেকবার আঁকতে হয় বুঝলেন, এই ছবিটা আমি আরেকবার আঁকছি বুঝলেন, এটা পরে এডিট করে নিন। So, to do this let us imagine that this is our ply, and this ply has this has direction 1 and this is direction 2, and we have direction x and direction y, and axis 1 with respect to axis x has an orientation of theta. Similarly, the angle between axis 2 and axis y is also theta. Now, let us draw a perpendicular to direction 1. So, to the axis 1 we are going to draw a perpendicular, and to axis 2 also we are drawing another perpendicular, and then we are joining them. So, let us imagine that we have a ply, and the ply has direction 1 in this direction and direction 2 along this, and it has x axis here and y axis here. So, the angle between direction 1 and direction x is theta, and similarly angle between y and 2 is theta. Now, we can draw a line which is perpendicular to axis 1, and then we can separate this part. So, if we draw the free body diagram of the separated part, this would look like this. So, if we look at this ply, then with respect to the x y system we have sigma x along this direction. So, we have epsilon sigma x, we have so let us use a different color to show the stresses. So, we have sigma x, and then we have sigma y along this direction, sigma x, sigma y, and then we have sigma s over here and sigma s over here, sigma x, sigma s. So, sigma x is basically our sigma xx, sigma y is sigma yy, and sigma s is tau xy. Similarly, so if I draw if I cut it and separate this part and draw the free body diagram here, what we see is we will see sigma x here, we will see sigma y here, and then we see sigma s here, and we will see sigma s here. Now, this angle is theta, and is in this inclined plane, as we know, this is perpendicular to direction 1. So, perpendicular to this we have sigma 1, and we know that this angle is theta, and this is theta also. Now, what we do is we would do the force balance in this part, and let us assume that this inclined edge has a length of L1. So, if we sum up all the forces along direction 1, so let us give it a name, maybe let us call it 1. So, or better let us call it A. So, in A, considering this part A, if we balance all the forces along direction 1 and set it equal to 0, this gives me this equation. So, along x axis we have the forces due to this stress sigma x. So, sigma x multiplied by this length, and this length is L1 cosine theta. So, sigma x multiplied by m, and we are saying that our m is equal to cosine theta and n is equal to sin theta. So, sigma x multiplied by m into L1, and then here we have sigma s. So, sigma s multiplied by n into L1, because this is our L1 sin theta, and then we have minus sigma 1. So, we have the component of this along x direction. So, it is sigma so the force here is sigma 1 multiplied by L, and the component of along x is cosine theta with a minus. So, minus sigma 1 L1 cosine theta means m we have already defined, L1 m, and also along this we have a component, stress component, which is sigma 6. So, a stress shear strain along this inclined line, which is sigma 6. So, plus sigma 6 L1 n, and this entire quantity is 0. Now, we can say that L1 we can just take out from all the sides. So, we get m sigma x plus n sigma s minus m sigma 1 plus n sigma 6 equal to 0. Similarly, we can sum up all the force along y direction and set that equal to 0, and that would give us sigma y multiplied by n into L1 plus sigma s, we have here sigma s multiplied by m into L1, and then we have minus sigma 1, its a component along the direction 1. So, sigma 1 multiplied by L1 into sin theta with a negative sign. So, sigma 1 L1 n, and we have sigma 6 L1 m, and that is equal to 0. So, that gives us n sigma y plus m sigma s minus n sigma 1 minus m sigma 6 equal to 0. So, let us call this equation 1 and let us call this equation 2. Now, we can solve this equation 1 and equation 2, and by solving we have to express sigma 1 and sigma 6 in terms of sigma x and sigma y and sigma s. So, first if you want to get our sigma 1, what we can do is we multiply sigma 1 with m and sigma 2 with n and sum them, and that would give us sigma 1 is equal to m square sigma s plus n square sigma y plus 2 m n sigma s. Now, our m is equal to cosine theta and n is equal to sin theta. So, m square plus n square equal to 1, and using this we get it. Now, our job is to get sigma 6, and to get sigma 6 we can multiply it by 1, we can multiply 1 with n, and we can multiply it by 2 with m and subtract, and that would give us sigma 6 equal to minus of m n sigma x plus m n sigma y plus m square minus n square sigma s. So, we could express sigma 1 and sigma 6 in terms of sigma x, sigma y, sigma s and m n. Now, we can draw another perpendicular here. With to the line 2. So, this we can draw another perpendicular here. So, this is also perpendicular our previous line. Now, we will take out this part and look at the force balance there to get other required relations. So, for that part, if we draw that separately, this gives us sigma y, and we have sigma s in this direction, we have sigma x, sigma s in this direction, and perpendicular to this we have sigma 2, and then we have sigma 6, and this angle is theta. Now, we have to balance the forces, and let us say that this length is suppose L2, and let us call this part as part B. So, if we again if we apply summation of all the forces along x equal to 0, that gives us this equation sigma s multiplied by L2 m minus sigma x L2 n, and then plus sigma 2 L2 n minus sigma 6 L2 m equal to 0, and then by writing the force equilibrium along y direction, we get another equation which is sigma y L2 m minus sigma s L2 n minus sigma 2 L2 m minus sigma s L2 n equal to 0, and let us call it equations 3 and 4. And again we can do the same thing, we can just solve these two equations and we can find out our expressions for sigma 2 and sigma 6 in terms of sigma y, sigma x and sigma s. So, doing the similar thing, we get from from equation 3 and 4 we get sigma 2 is equal to sigma x multiplied by n square plus sigma y multiplied by m square plus 2 m n sigma s. And we from this, by solving these two, we get sigma 6 once again, and this sigma 6 should be what we got from here. So, from this part, from equation 1 and 2, by solving whatever sigma 6 we got, same thing we should get here also. So, if the sigma 6 that we get from these two equations is different from what we get here, that means that we have some error in the formulation, otherwise they should give the same sigma 6. So, now we have got sigma 1, sigma 2, sigma 6 all in terms of sigma x, sigma y and sigma s and m n. So, by solving these two, what we get, if we write this in a matrix form, it looks like this. So, this is our stress transformation. Now, we have to define the strain transformation. To define strain transformation, let us imagine that we have an axis system x, y, and we have another coordinate system 1, 2. And let us imagine that we have a point here. So, with respect to this, if I draw a vertical line to the x y, what we get here is x, and if I draw a vertical line here, what we get here is y. And similarly, if I draw a vertical line on the axis 1, so you get x 1 here, and if I draw a vertical line on axis 2, we get y 1 here, and this is our theta, and let us call it a point P. So, from this diagram we can say that x is equal to our x 1 m minus y 1 n. And similarly, y is equal to x 1 n plus y 1 m. So, we can write x y is equal to m minus n, n m, x 1 y 1, and we can invert this relation and also can write x 1 y 1 is equal to m n minus n m x y. It is just inversion of this relation, and which gives us this. Now, we already know that we have 3 strain components epsilon x, epsilon y and epsilon x y, or in the 1-2 system epsilon 1, epsilon 2 and epsilon 6. So, with these findings we have to now do a transformation between these two stresses. Now, before that, because we know that our x in terms of x 1 and y 1 is this. So, if we define a movement along x and if we call it y, call it u. So, u which is a displacement along x can also be written as, or to if you write other way, if we define a movement along one direction and which we call it u1. So, u1 with respect to a movement along x and y can also be written as mu plus nv. Similarly, v1 which is a movement along the direction 2 can also be written as mu minus of mu plus nv. So, e1 v1 are movement along x1 y1 and uv are movement or displacement along x and y. So, they also follow the same relation. Now, let us define a strain epsilon 1. So, epsilon 1 as per definition should be derivative of displacement along x1 with respect to x1. So, we can write using the chain rule of differentiation as del u by del x into del x by del x1 plus del u1 by del y multiplied by del y by del x1. And now, we can write u1 in terms of u and v. So, mu plus nv and del x by del x1. If I look at this relation, from this del x by del x1 becomes 1, because our x is equal to x1 m minus y1 n. So, del u by del x1 is equal to m plus again we have del by del y and u1 is equal to mu plus nv and then del y by del x1 which we have here del y by del x1 is also is n. Now, if we differentiate this mu with respect to x, we have m multiplied by del u by del x and we know that del u by del x is x. Similarly, here we have n multiplied by del v by del y and we know that the del y del u v by del y is epsilon v epsilon y. So, del u by del x is epsilon x and del v by del y is epsilon y. And this term will give us mn multiplied by del v by del x and this will give us mn multiplied by del u by del y and we know that del v by del x plus del u by del y is epsilon x y or epsilon s. So, this entire quantity can be written as mn multiplied by epsilon x plus mn multiplied by epsilon y, not mn, it is m square. And then we have mn epsilon s. So, to do this we use the relations epsilon x is equal to del u by del x, epsilon y is equal to del v by del y and epsilon s which we also call as gamma x y is equal to del u by del y plus del v by del x. Similarly, now we have epsilon 2 which is equal to del v 1 by del y 1 and this we can write as del v 1 by del x multiplied by del x by del y 1 plus del v 1 by del y multiplied by del y into del y 1. Now, we know that v 1 is equal to minus nu plus m v and del x by del y 1 is minus n and similarly we have here also minus nu plus m v and we have del y by del y 1 is equal to m. So, again if we write this equation, finally it would give us n square multiplied by epsilon x plus m square multiplied by epsilon y minus m n epsilon s. Now, our job is to transform epsilon 6. So, epsilon 6 by this definition would be del u 1 by del y 1 plus del v 1 by del x 1, and we have del u 1 by del x multiplied by del x by del y 1 plus del u 1 by del y multiplied by del y 1 plus we have del v 1 by del x multiplied by del x by del x 1 plus we have del v 1 by del y multiplied by del y by del y 1. Now, we can write del by del x, and this is equal to m u plus n v, and del x by del y 1 is equal to minus n, and this we can again write m u plus n v, and del y by del y 1 is equal to m, del y by del y 1 is equal to m, and here again we have del x of v 1, and v 1 is equal to minus n u plus m v, and del x by del x 1 is m, plus we have del y multiplied by v 1, and v 1 is equal to minus n u plus m v, and del y by del y 1 is so this should be x not y, excuse me. So, this is del y by del x 1, and del y by del x 1 is n as per this. N. Now, we can again simplify the entire relation, and that gives us the final relation, and the relation becomes minus of 2 m n epsilon x plus 2 m n epsilon y plus m square minus n square epsilon s or epsilon s or epsilon x y. So, epsilon s is equal to gamma x y, not epsilon, gamma x y. Now, we can write this relation in this form epsilon 1, epsilon 2, epsilon 6 as m square, n square, m n, n square, m square minus m n minus of 2 m n plus 2 m n m square minus x n square, and that is right multiplied by epsilon x, epsilon y and epsilon s. Now, if we compare this relation with the stress strain relation which we got before, if we look at this matrix which transforms the strains with respect to x y to the strain with respect to 1 2, if I compare this matrix with the previous matrix which does the strain transformation, we can see some difference. We have 2's here and we do not have 2's here, whereas here we do not have 2's, but here we have 2's. Now, if we want to make the previous matrix applicable here, what we can do is we can define the shear strain relation little bit in a different way. So, instead of writing epsilon 6, if I write epsilon 6 by 2, then this relation changes and it looks like this. So, we define a new shear strain here, and this we call tensorial shear strain. This we call tensorial shear strain. And this matrix, this transformation matrix we call T. So, now with the help of this we can with the help of this we can rewrite epsilon 1, epsilon 2, epsilon 6, the relation that we got q11, q12 0, q12, q22 0, 0 0, and here in the shear part, shear strain part, instead of using epsilon 6, let us use epsilon 6 by 2. Now, so accordingly to keep the value of sigma 6 remains same, we multiply q 6 by 2 here, q 6 by 2 here. Now, we already know that these sigmas are in terms of sigma x, sigma y, sigma s are this sigma 1, sigma 2, sigma x equal to this transformation matrix multiplied by sigma x, sigma y, sigma s. Sigma 1, sigma 2, sigma 6 is equal to this in terms of the transformation matrix, and similarly we will transform our write our epsilons in also the transformed form, and this we know epsilon x, epsilon y and epsilon s. Now, we can bring it this side, and now we can write T inverse multiplied by q11, q12 0, q12, q22 0, 0 0 to q 6. And then now this T matrix has a property that T inverse is equal to T of minus theta. So, now this relation can be written as sigma x, sigma y, sigma 6 is equal to whatever we get after this multiplying this with Q matrix with T, we write this as q x y, q, and again we adjust here epsilon s. So, after doing all the adjustment, whatever we get here we can write it in this form. Epsilon f y epsilon s. So, this becomes our new constitutive relation with respect to the x y system. So, this was the constitutive relation with respect to 1-2 system, and this is with respect to the x y system. So, to keep things shortened, we write q with respect to the 1-2 system as q11, q12 0, q12, q22 0, 0 0, q66, and when we write Q with respect to xy system, this is the expanded form. So, this is our transformed constitutive relation, where Q is the stiffness matrix with respect to the xy system, and these are the stress and strains with respect to the xy system. So, with that we would conclude this lecture today. Thank you.